move. Yay, it worked. So, are you guys okay with the elevator stuff? Where if you're in an elevator, we can do a calculation. Yes.
What's the name of Darth Vader's wife? Elevator.
Oh God, it's terrible.
You see this in the fractions. We problems for all space or 10 kills.
Okay. Let's maybe do one elevator problem with numbers, and then we're going to do the block problems, and then the very last thing is just these last two. These might look familiar to you. These graphs, we have done them before. They're just going to be the answer will be slightly different now because instead of talking about just acceleration, we're going to talk about force. But they're pretty much the same question we did before, back in kinematics. So I don't know. We can just do 39, I guess. Hopefully you attempted it. Looked at it. Albert is standing on a scale in an elevator. Maybe we'll do two. There's some that I just have percentages. So Albert is standing on a scale in an elevator, traveling upward. So as always, I would recommend making a diagram. Oh, this marker's not very dark, is it? Okay, he's traveling upward at a constant speed of 18 meters per second. This is a constant speed. And right now, this is kind of like the before. What does the scale read? Okay, this is 39. So it reads 735 newtons. Now that's big information to know. Yeah, these are weird scales that are calibrated to read out in newtons, living in a SI universe here. Now that's the force. Now remember what a scale tells you is how much upward force is the scale exerting on you. That's what a scale says. Okay, it does not tell you anything about gravity, really. Well, I mean, implicitly it does. But if you, again, back to the outer space thing, if you were in an outer space elevator with no gravity anywhere and it was accelerating you up at whatever 20 meters per second squared, the scale would have a reading. The scale would tell you, oh yeah, you're heavy. You're roughly twice as heavy as you are on Earth if you're accelerating that fast. Everyone okay with that? Makes sense? Okay, so, but if you're going at constant speed, then the scale is just balancing out gravity. Is everyone okay with that? So what information do we have right now? We know that's the energy value. So right now we could actually calculate, if we wanted, your mass. Why don't we do that? We might as well. Oh, great calculator. What is 735 divided by 9.8? Turns out it's 75. Exactly. Really? Let's see, how many pounds is that? Okay, it's 165, yeah.
I'd say 140.
Lit. Okay, so there's your mass. Now let's see what happens. There's before, here's after. Now why split it up into two different periods? Well, before we were going at constant speed, and so that was able to give us information. Remember that fancy word, inertial reference frame, right? We're in an inertial reference frame, so we actually know that these balance out. Net force is 0. But after, the elevator starts coming to rest. So if I was traveling upward and coming to rest, what direction is my net force?
Down.
Down. Don't overthink it. Just think my velocity vector points up and it's getting smaller. So therefore the acceleration is the opposite direction. Anytime you're slowing down, your net force is opposing your velocity vector. Anytime you're slowing, so again, that's a good one to know. If you're slowing down, the net force points in the opposite direction of the velocity vector. So maybe the first thing I look at is, okay, I just know that F net points down. Before I even do anything else, I just know that has to be true. If I come to rest over a 3-second period, so if my velocity goes from 18 to 0 over a time period of 3 seconds, what does all that information combine into telling me? 6 meters per second acceleration. Cool beans? Well, that means, well, hey, I don't know, you can do force diagram, then the equation, or do it the opposite way. I kind of like doing the force diagram first. Here's the guy. Now let's go back to what are we answering? Well, we're answering the question, how much force does the scale exert on the dude in order to have this be the acceleration, right? So, how big is that vector?
Well, it's
735. Are there any questions on how I'm getting that number? You sure? Okay, again, gravity doesn't care, right? Gravity's unaware of anything. So just, okay, it's still 735. Now this vector here, should I make it big or small? Small? Okay, it has to be smaller than the 735 in order to generate this downward net force. This is what I'm solving for. This is the force from the scale. That's what the scale tells us. And so I can say, when I write F net equals MA, okay, well, according to this diagram, now here's where, okay, I need to take a little sidebar here. If I want to call this the positive direction, which a lot of people want to say, I'm always going to say up is positive. Then, if you do that, the net force is this minus this. But then you have to make sure that this number is negative. However, there's nothing wrong with saying this is the positive direction. Nothing wrong with that. This is the positive direction. In that case, the net force is this minus this, and you can call the acceleration. I'll show you both here. Let's see how it works out. You can choose how you want to kind of process that. Let's start with saying that I'd probably prefer just to go this direction. I'd say this is my positive direction. So then I'd go 735 minus the force from the scale equals his mass. What's his mass? 75. The acceleration was 6. And so when you solve that, it's just ends up being 735 minus 75 times 6, and you get 285. Okay. Let's suppose I'd gone the other way. What if I'd said that up is the positive direction? Well, I would have just gone force of scale minus 735 equals 75 times negative 6, and not surprisingly, you get the exact same answer. 285. So, last little thing here. Can we express this as a ratio? Can we say that, oh, so-and-so, Albert, he feels some percentage of his usual weight? Is that easy to do? Yeah, it's super easy. You just go, if you went 285 is how much force he's feeling right now. Compare that to what he usually feels, which is 735. And let's see, divide by 735. So it turns out that Bob or Albert, whatever, is right now is feeling about 38.8% as heavy as he usually does. So somewhere in the ballpark of a third of his usual weight. Not quite moon status, but not yeah, he'd feel pretty light. Now, is that what really happens in real life? That's pretty extreme. That would probably, I don't know, that might make some people feel sick. So why is that such an extreme result? Well, I mean, going from, first of all, 18 meters per second is pretty fast. But also, if you were going that fast, which I'm actually curious, floors, maybe they do have to go that fast. But you certainly won't be slowing down over just 3 second period. They'd probably spread that slowing down over a longer period of time. You can see if that number was bigger, this number would be smaller, which would make this number bigger. And so you'd feel more closer to your regular weight. All right, you guys all okay with that stuff? Makes sense? Let's do one more elevator. Let's look at 42. Just to make sure there's no confusion over.
Yeah. That doesn't give us an exact speed, but it goes from the first floor to the 95th in 42 seconds.
Oh, what does it go? From first to 90, what? So each floor is about 10 feet, right?
Yeah.
So from 95 floors times 10 is 950 feet. So divide that by roughly 3. So it's something like 316 meters. And how long does it take?
42 seconds. It says it goes 1,260 years a minute.
Oh, how many? 1,000?
260 years a minute.
So divide that by 60. According to that, it's 21 meters per second. I guess what, is a floor really way more than 10 feet?
Is it count on like the structure bits? It's probably like 12 to 13.
Okay. That's what I'm not sure about but if it says 1,200 meters in 1 minute, you said 1 minute, right?
1,260 meters a minute.
Yeah, that'd be 21 meters per second. So yeah, okay, kind of close to that problem. Okay, so 42 says, it's the same kind of question. But it's the same thing. Like, I'm sure that elevator slows down over like maybe a 10, 20 second period. And so it doesn't actually feel that extreme. Yeah, all you gotta do is, like general principle in physics and kinematics is, you spread that acceleration over a longer time period, it's gonna be like less acceleration. You're gonna feel it much. So 42 says you're in an elevator at rest, and as the elevator starts accelerating upward, so right now, right at that moment, I can go, okay, that means the net force has to point up because it's accelerating upward, right? The scale is reading 70% greater than usual. So let's think about that. 70% greater than usual. What's usual, by the way? Usually, this is you on your day-to-day life. It's you have mg pulling you down, and the floor pushes back with that same amount of force. Cool beans? Usually your net force is 0. Right now, for me, my net force is 0. But right now, is there more or less force pushing up? More. It's 70% greater than usual. So how do I write that? How do I write 70% greater than usual mathematically? Anyone?
Yeah.
mg times,
0.7.
that would be 70% of my usual.
So you're actually times 70%.
1.7. Yeah, so it's basically what you're totally correct. It would have been like, hey, that's my usual plus 70% of my usual, and it's more concise to write that as 1.7. Cool beans? So same thing, like, I'm going to sell something at a 25% markup. Just you'd multiply by 1.25 to add 25%. Okay, so then it says, what would be the acceleration that generates this sensation? So I feel a little bit less than double my weight, right? I'm not feeling quite double as heavy. So, this is actually a very easy question. I can write F nat, famous equation, F nat equals ma. But according to this, F net is 1.7 mg minus mg. What's 1.7 mg minus mg? 0.7. Banana theorem. 1.7 banana minus 1 banana make 0.7 banana. So applicable, wow. Now here's the cool part, because you might have been wondering, wait, don't we have to know how heavy you are for this? It turns out, cancel away. No, the mass does not matter. So if me and Shaquille O'Neal, that's a heavy man for those of you guys who don't know who that is, if we're in the elevator together, we would both feel this percentage-wise, we'd feel the same proportional change in our weights. So if I'm like, oh, I'm feeling 70% heavier, Shaquille O'Neal is also going to say, I am feeling 70% heavier. Now, in terms of the actual change, for me, that might be, oh, I'm feeling an extra, 100 pounds or something, whereas he is going to be like, oh, I'm feeling an extra 200 pounds. So, but proportionally, in terms of ratios, it's the same. Cool beans? All right, so every other question, they're all the same. So it's the same principle every time. Draw the force diagram carefully. This is the most critical step. This is the part that's easy to mess up. But every time you have your force diagram, once you're pretty sure you have it written out, you write F net equals ma, you put in your knowns. Okay, occasionally you might have to, like on our previous problem, you might have to calculate the acceleration using some kinematics, but for this, the final answer is 0.7 g. So the acceleration was 70% of 9.8. So whatever that is, 0.6. This is, of course, is the most interesting way to write it. So accelerating upward at 70% of g with that magnitude of acceleration, it's 6.86, would make you feel 70% heavier. You'll find that when you do the calculation for what acceleration is necessary to feel, say, 10% lighter, you'll figure that out. You'll get the answer. So, the answers, you'll end up getting answers like this. All right, let's move on. So, just a couple more things. Jiba, were you raising your hand?
How do you cancel the m's? The masses?
Right at this step?
Yes.
Dividing both sides by m.
Okay.
So, as long as m isn't 0. Who knows? What is the only object? Well, I should say only. What is the most familiar object that has 0 mass? It's in this room right now.
Air. Light.
Light, yes. Photon. Light.
The whole room is in tears.
Yeah, so none of this would apply to photons, because like that step, for example, none of this really makes any sense in the context of like a massless particle. Although interestingly, I know I was rambling a bit about general relativity yesterday. Gravity can bend light. Pretty fascinating. Even though, like, wait a second, I thought like gravity only worked on mass. No, actually, light can bend due to gravitational field. It's the bending of space itself, space-time itself. You guys ever heard of that? There'll be like say there's like a big mass here. This could be a big mass, or like it could be, I don't know, a galaxy, whatever. And let's say there's some like stars over here. They've shown this experimentally. And here's the observer. Here's us. And it's like, oh, the light from these stars we can't see it. It's blocked. But no, because the light goes bend, and you're like, bruh, I see you. They can show they call it gravitational lensing.
So where do you see the light? You see like where it is?
You would think it's coming from like over here.
Oh,
You ever seen, you guys have, like, if you've ever fished, you know this idea, right? It's not the same exact thing, but here's the ocean, or the lake floor or whatever. Here's Mr. Fishy. Here's me. I see Mr. Fishy, but actually the light bends. Kind of like that.
yeah.
And so where do I think the fishy is? I imagine he's somewhere, well, I guess it's a bad diagram. This is where human perception is kind of interesting, because I think I would kind of see him as being closer to the surface, I think. That's how I would perceive it. But anyway, you guys have seen that before, right?
Yeah.
Light bends when it,
Interesting. Like I think at least some of those fish spread, like the closer you are, like it's almost on like top of the fish, like the less of the less your perception is off. At least in my perspective.
oh yeah, because the law would be, when you look at this mathematically, here's the surface normal, and then you have these two angles, and then you have these two like indices, how fast light travels in those two media, and it's like if you're interested in this, it's called Snell's law. It's pretty interesting. But yeah, so if you're like right on top of the fish, if the fish is like here, then if you look at the math of it, yeah, there's not much bending that occurs. But if the fish is over here, yeah, more of a bending occurs if you look at that formula. So, anyway. Oh, the blocks. 46. How are we doing for time here? Okay, we're doing fine. So these problems should be pretty easy, guys. They're not difficult problems. Okay, there's just a little trick to them that makes them a little tricky. So don't overthink them. They will be confusing if you overthink them. Not to say it can't be kind of fun to overthink some things sometimes, but if you want to just get the answer efficiently, they're very simple. So 46 says you got a 40 kilogram block and a 60 kilogram block. And you push, here's you. You push with a 300 Newton force. The question's asking two things. How much force does he exert on him? And how much force does he exert back on him? Third law for, every force is met with an equal and opposite force. So we know that, if you've heard of that, or I just told you actually, I guess, if you haven't heard of it, these are going to end up being equal and opposite forces. However, that's really just, we're going to see that bear out in the math here. So we don't need to presuppose that, but it is going to be true that they're going to, when I push on, if I push you, I'm also pushed back. We'll do some problems later on, like astronauts out in space. Oh, Albert pushes on Bob, and they both go in different directions. So, same idea. Anyway, who thinks they know the trick to solving this? Maybe I'll phrase it differently. How fast will this thing accelerate when he pushes it? Anyone? No one? What if he was just pushing a 100 kilogram block? Is there any difference really? No. They're going to move you all agree they're going to move together, right? Just common sense wise. When he pushes them, they're going to move together. So what's stopping me from just being like, I'm going to treat this like a single 100 kilogram block. Nothing's stopping me from doing that. So therefore, I can say, well, if I visualize this system as a 100 kilogram block, then it's actually very straightforward, isn't it? There's the net force. I can go F net equals MA. By the way, technically, is that the more complete force diagram? Gravity and normal force, but they cancel out. We get to ignore those, okay? What's the net force? You said MA. The mass is 100, so that tells us that the acceleration is 3 meters per second per second. Okay, what do I do with that? Now we come back to the original scenario. Now we have extra information, right? We know that each block is accelerating to the right at 3 meters per second per second. So now let's draw these guys' force diagrams. Let's look, who do we want to look at first? He's going to be easier to look at. 60 is actually a very easy one to look at because I just go, well, Mr. 60 kilogram block, from your perspective, who's pushing on you? Yeah, he's like, dude, this guy's pushing on me. If I call these block A and block B, and I ask block B, who's pushing on you, Mr. Block B? He's going to say, well, it's block A. He's doing it. That's the culprit. So this is the force from block A. But wait, that's a really easy diagram, isn't it? F net is just that force equals MA. So he must be feeling 180 newtons of force. Does that make sense to everyone?
Yes.
If you're a 60 kilogram block and the only force you're really feeling, the only net force is 180 newtons, then you would accelerate at 3 meters per second, which is exactly what we know is happening.
I guess, why is it 60 and not 40?
I'm talking about this block.
Okay, I was just thinking like, since.
Oh,
never mind, I get it.
I'm reading this as the force exerted by block A.
Yeah, I get that.
Okay. All right, now let's look at block B, block A, 40 kilogram block. This is why I like to put the mass inside of the block so I can just keep it straight. Okay, this one's more complicated though. How many forces is he feeling other than the gravity and the normal force that cancel out? He's being pushed to the right by how many newtons? 300. And he's being pushed to the left by, we're going to solve for that, force from block B. By the way, you already know the answer is going to be 180. Full disclosure, it has to be Newton's third law. Okay, but let's just see, does it actually bear out in the calculation? Yeah, if I write F net is 300 minus the force from block B, his mass is 40, and his acceleration is 3, and I solve that, I get 180 newtons, as expected. Ah, man, great. Everything works out. It all makes sense. Hopefully it makes sense. So we're sure that, so recap this procedure. It's first figure out the acceleration by lumping the blocks together into a single block. Once you know the acceleration, come back and draw separate force diagrams for the two blocks individually and use that acceleration that you found for your calculation, okay? Okay, we only got a couple of minutes, but luckily 52 is actually a very easy question. It looks intimidating when you read it, but it's actually very simple. So the graph below. So guys, tomorrow in class, the practice quiz is up. If you have time, I'd recommend maybe doing the practice quiz outside of class, and then you can use tomorrow's class time to just finish this or whatever you want to do. But Stephen King's The Mist. Okay, so this graph, roughly speaking, looks like this.
Sorry, it's 33.
Okay, there's my kind of crappy redrawing of the picture. But hopefully you guys recall doing these problems from before. Before, the question you were asked was, what was the acceleration at this event when it changed velocity? Okay, now I'm just going to ask you, what was the force? So I'll just remind you of the procedure here. So what was the velocity before the collision? Remember, the collision happens at time 2. So what was the velocity during this time period? Yes, 1.5 meters per second. What was, everyone understand that? It's just the slope. I went 3 meters and it took 2 seconds. After the collision, I went, what? I guess I should have put this in here. -1 meter over 4 seconds. So negative 0.25 meters per second. Great. So my change in velocity was, well, technically it's negative. I'm going from positive to negative then. It's negative 1.75. Does everyone understand that? Sure?
Yeah.
Okay. So if I know this, and I know that this event here took 25 milliseconds, so 25 thousandths of a second. Everyone okay with that? If that's written in the problem here, a slow motion camera reveals that the collision took place over a period of 25 milliseconds. Sure that makes sense to everyone? Okay. So what do? I can get the acceleration as change in velocity over change in time. So negative 1.75 divided by 0.025. What? So that would be, I think that's what, negative 70? Use a calculator if you're not sure. And then the last step is what? If you know acceleration and you know mass, if you know acceleration and you know mass, the net force in the dummy was his mass times acceleration. So plug in 75 and negative 70, and there's your force. Weeds? Okay. And again, new marker. Hopefully that was all readable.